Welcome back to Newtonian, and in today's lesson we're going to be covering the chapter of waves. Now, waves play an integral part in the A-level curriculum, and a lot of questions come on it every year. So what we first of all need to know is some of the fundamental concepts about waves. So the first thing in waves is a progressive wave. What exactly is a progressive wave? Well, a progressive wave is simply any sort of wave which moves through a medium and ends up transferring energy. So a progressive wave is a wave that moves through a medium and transfers energy. So this could be potentially a sound wave or a wave through the sea, any sort of wave which essentially just moves through a medium and ends up transferring energy. Now, one of the key concepts you need to first remember is that whenever a wave is transferring something, it's only transferring energy. It's not transferring matter. And one great way I like to remember this is imagine you and your friend are holding a piece of string. Okay, that's your hand, that's your friend's hand, okay? And in between you have one piece of string. Now what you guys do is you blindfold your friend here and you tell him to shut his eyes closed and you can still see the string. And what you do is you, at a random moment, you shake the string. So then now the string has waves on it. Now on this string you also have put one bead here and one bead here, okay? Now these beads essentially will just move up and down, right, at the position they're at. So this bead will go up, this bead will go down, but this bead will not have actually moved across, right? Yet, my friend who has a blindfold can feel this wave reaching him. In other words, something has reached him, but material hasn't reached him because the beads only moved up and down, they didn't actually go to him. In other words, the only thing that could have been transferred to him and has been transferred to him is energy. In other words, waves transfer energy. They don't transfer matter. So that's one key concept, and I think we've got a good hold of that now. Now, this is where things get a bit more fun. So, what are the two types of waves there are? The first type of wave there is a longitudinal wave. That's a longitudinal wave. And the second type you have is a transverse wave. Now these are the two types of waves that there can be. Now let's go through these one by one. So the first one that I want to go over is this longitudinal wave. Now what exactly is this longitudinal wave? We can see that there's all these white circles everywhere. Now what do these circles first represent? These circles are just air particles, okay? Now when we have our air, and if we zoomed into our air, in reality we put one particle here, we put a particle here, we put a particle here, here. They're all very randomly arranged, right? Whereas what we see here is not a random arrangement. So what's happened? The way I want you guys to visualize this is we've got a speaker cone here, okay? Now this speaker cone is moving forwards, it's moving back, it's going forwards, back. Now the speaker cone now collides with this particle. These particles here, this wall of air. Now when it does that, it hits them forwards, right? When it hits them forwards, these particles hit these particles, they come closer to them, they smash into them, these ones then hit the other ones next to them, and this causes an area of higher density to be formed. Right? This causes an area of higher density to be formed. Now this higher density area is something known as a compression. It is known as a compression. Now when all of these particles are bunching up together, because one's hitting the other, they're hitting each other, this causes another thing to be formed. Because all of these are bunched up here, there's a massive gap here now. Now this massive gap here, or an area of lower density, is known as a rarefaction. This is known as a rarefaction. So the density at a compression is high, whereas the density at a rarefaction is low. And that's pretty much it about the structure of this of a longitudinal wave. Now, what can we actually understand from this whole graph? If I were to say we want to get a few values out of this, what are they? Now, a few of the things that you can actually learn from this graph is the amplitude, the wavelength, these two. These are the two concepts we need to figure out using this diagram. Now, how are we going to do this? It's easy. Let's start off with wavelength. How are we going to work out wavelength using this diagram? Well, what we do is we look at a compression, one compression, and we look at the adjacent compression to that. So this is the first compression. The next compression we can see is here, right? That's the second one. Now we go to the middle of these and we look at the distance between. And that's wavelength. Essentially, wavelength on a longitudinal wave is the distance between two adjacent compressions. What if I don't want to use compressions, for example? Well, what do I do now? It's easy. All we do is we look at a rarefaction now. We look at the middle of the rarefaction, look at the middle of the other rarefaction. We just look at the distance. The wavelength in this case is just the distance between the centers of two adjacent rarefactions. It's essentially, you look at the same point on the next wave. The distance between the same point on one wave and the adjacent wave. That's all you're doing. Diagram looks a bit complicated. Really, it's quite simple. Now, the next thing we want to work out is the amplitude. Now, before I go there, what exactly is amplitude? Now, to understand this, let's just imagine a particle here. Now, this particle, when I say this starts to oscillate or vibrate, it moves, say, left to right. Okay, so it moves this much to the right, and then it moves this much to the left. Now, the distance that this particle moves to the right or the left is known as displacement. We can represent that by a d. Now, the maximum displacement, or the maximum amount that this particle will move in any one direction, is known as our amplitude. Okay, it's simple as that. Displacement is the distance that the particle is moving. So if the particle moved here, the displacement would have been this much. Okay, whereas amplitude is the maximum displacement of the particles. So now, if we look back at our diagram here, we know that our amplitude here will be how much these particles have moved from their original position. So if in an exam question we were given, say, that the particle at the equilibrium position was here, or maybe here, the distance that it's moved during the rarefaction would be our value of d. That would have been our amplitude. So essentially, how far this particle has been displaced from its equilibrium position to its new position is our amplitude, right? It's very unlikely you'll be asked to figure out the amplitude for a longitudinal wave, because it's not exactly very easy to just look at one of these diagrams and tell what the amplitude is. But the wavelength is something that you're probably going to be asked, so I'd recommend you having another watch of this and just trying it out yourself. Now we've understood the key things that we can work out from this graph. Let's just come up with a quick definition. Let's let's just define a longitudinal wave. Now, what I don't like is having to memorize definitions. So let's try and understand this definition instead, okay? And then if you have to memorize it, I guess you do, but I think we can work around that. So with our longitudinal wave, we know that these particles are moving left to right because we had a speaker cone here which is pushing forwards and then pushing backwards, which meant that it hit the particles straight, and then the particles hit the next one and the next one and so on, right? So that means we know our particle is moving this way and is moving this way. Now, what direction is the energy transfer? So if I'm sitting here, if I'm sitting here and the speaker cone is here, I can still hear the speaker, right? And that means something has been transferred to me. And we know that something is energy because this is a progressive wave. And hence, it doesn't transfer matter, instead it transfers energy. In other words, the energy has been transferred from here to here. So we know energy has been transferred from here to here. And this is energy. And we could say these are the oscillations. This means, from the arrows, we can see that these are clearly parallel. The oscillations are parallel to the energy. So let's come up with our definition now. Longitudinal waves are waves which have oscillations which are parallel to the direction of energy transfer. It's as simple as that. A longitudinal wave is a wave which has oscillations which are parallel to the direction of energy transfer. As simple as that. That's kind of all you really need to know about longitudinal waves, realistically. I guess an example of these could help too. Now, the most common example of a longitudinal wave is sound, but that's a bit too obvious for an exam question. Another sort of, I guess, longitudinal wave that does come up at times in exams is a P wave. Now, P waves are essentially longitudinal waves which are formed during earthquakes, and these are transferred throughout the Earth, right? So P waves is a less common example of a longitudinal wave. And yeah, that's all we need to know about our lovely longitudinal waves. Now let's move on to the next one, which is a transverse wave. Now, transverse waves are much simpler to understand than longitudinal waves, because transverse waves are kind of what we imagine waves to be. We've seen this squiggly line throughout our lives for waves, right? Let's just go over it now. So, what do we have here? Now, the way to understand a transverse wave first is actually using a string. Now, we can have the string attached here and here. Now, this string has two beads attached to it. One here, and our second bead here. Okay? Now, when we, so let's just have this bead a bit further down. The other bead here. Okay. Now, when we start to switch on an oscillator, which creates a wave, we get something like this. Okay? And this causes our beads to be somewhat like this. Blue bead is up here, whereas the pink bead is down here. So what we've seen is that my bead has moved up here, whereas my bead has moved down here to reach that point. In other words, the oscillation is going up and then down, up and then down. This bead at another point, in another frame, would be here, whereas this bead in another frame would be here. In other words, all that's happening to the material is it's moving up and down, up and down, up and down. So if I were to represent the oscillation on the particle, it's going up and then it's going down. What about the energy transfer? Well, we talked about the example of the string at the start too, where I'm holding the string here and my friend is holding the string here. And we realized that the energy is being transferred along the string into my friend's hand. In other words, the energy transfer is to the right. So we've got energy transfer like this. Now what you see forming is essentially a right angle here, right? That's a right angle between the oscillation of our particles or our matter and the direction of energy transfer. This allows us to come up with a definition of a transverse wave. Let's do that. Let's rub this off and let's define a transverse wave. A transverse wave is a wave whose particles oscillate perpendicularly to the direction of energy transfer. Transverse waves are waves who have particles which oscillate perpendicularly to the direction of energy transfer, and we can clearly see that here. Now, what are a few things that we can learn from the diagram of a transverse wave? Let's think about this. Now, the two things we looked at in our longitudinal wave diagram was amplitude and wavelength. Now, how do we do it here? It's a lot more easier here. For amplitude, which was the maximum displacement, all you have to do is just look at the height. The height of a crest or a trough is your amplitude. That's your amplitude. Now the next question that begs is, what is the displacement? Now the displacement of this can be, for example, when the wave reaches this point, that's your displacement, that's your displacement, because displacement is by how much a particle has oscillated. So if the particle has oscillated till here, that's your displacement, when the maximum point that a particle has been displaced is your amplitude. Cool, so we've learned this property. How about a wavelength? How do we figure that out? Now for a transverse wave, we just need to find this point here and the same point on the next wave. So the next wave would be somewhat like this, right? So the same point on the next wave, the starting point is here. So the wavelength will essentially be from here to here, right? That's one wavelength. What if I don't want to use that point? What if I want to use the tip? Now, a lot of students get very confused here. What they'll say is from here to here. No, that's wrong. The wavelength is the adjacent point on the next wave. So the next wave, the same point will be the crest. So this is also one wavelength. That's one wavelength. So essentially now we figured out how we find the wavelength and the amplitude. Now the final thing that we need to know about transverse waves is examples of transverse waves. Now what are some examples of transverse waves? One example of transverse waves, and the most common, are EM waves.
Now, EM waves could be your gamma waves, your X-rays, your, say, light, UV, infrared, all of this, right? The next more common one is you've got water waves. And then another type that you have is S waves. Now, S waves is something that can come up a bit more often because it's very niche, to be honest. S waves, most students don't even know about it that well. So this could come up as a higher order question. So what sort of wave is an S wave? An S wave is a transverse wave, and it's generated during earthquakes. Right, lovely. So we've covered what a longitudinal wave is, some examples of longitudinal waves, how we can interpret the diagram representing longitudinal waves, and then we've gone on to transverse waves. We've understood the definition, we've understood how and why that definition comes to be. Then we've gone over some examples, and we've also figured out how we can find the amplitude from a transverse wave diagram, as well as its wavelength. Right. Thank you so much for watching the video, and I hope this clarifies some of your doubts and you've learned something new. Do keep learning, and please do keep watching Newtonian. Thank you.